All right, so now we need to look at our last case of dealing with limits, and these are infinite limits. But first, let's review a little bit what we've already done. We've looked at a case where the limit exists on a continuous graph. So that's something where you have some kind of a curve that goes on forever, and if I decide to take the limit here at C, well, the right-hand limit exists and points to n. The left-hand limit exists and points to n. And if I plug c into the function, the f of c exists and points to or equals n. And so that's the perfect scenario that has everything exists and everything is right where you want it to be. So we have, let me write it out. So that's a perfect world, and we really like it when that happens, but it doesn't always happen. And then we have another scenario to look at where the limit exists but the function doesn't, and that's a curve or a graph. So say the same curve, only I have a hole and then the curve continues on. So the limit from the left, or excuse me, from the right exists and points to L. Let's call this D. So as x values approach D, the limit exists from the right and equals L. The limit also exists from the left and equals L, but the limit or the function of D does not exist or does not equal L. In two scenarios, one is it's just a hole with nothing anywhere, and the other is that you might get a point someplace elsewhere on the graph but not connected to the curve you're looking at. So in this case, you have the limit as x values approach c from the left of f of x exists and equals L, and you have the limit as x values approach c from the right of f of x equals L. So the limit exists. In this case, we would be able to say that combined the limit as x values approach c of f of x equals L, because the left-hand and right-hand limit exists, therefore the just general limit exists. But the function doesn't exist. This is also called a removable discontinuity. And let's come back up here. This first situation is a continuous function. And then at C if I want to be extra careful. And this would be a removable discontinuity at D. Okay, so another scenario is that the limit does not exist at F and the function may or may not exist. So this is a scenario that looks like maybe a skip function. We have something happening on the right-hand side. You have something happening on the left-hand side at what I say F, but there's no limit. I can't choose a value. I can't choose an output to say, oh, it equals n. It just doesn't exist for me to do that. I may have a function exist. It may exist at, the function may exist at one or the other of these, not both, or it may not. That's not really dependent. In this case, when something like this happens, we have to talk about the limit from one side and the limit from other, and they're going to equal different things. So this would be the function of D, F, may or may not exist, right? It may or may not exist. But it's definitely not equal to the limit as x approaches c from the left of f of x, in the case I've drawn here where I have no f of f value, or the limit as x approaches c from the right of f of x. Okay, so in this case I have no function existing, right? But I have the left-hand limit equaling, let's call this let's call this n, and I have the right hand limit equaling p, say. Okay, so the right hand limit points to p, the left hand limit points to n. The function could be non-existent. It could be d and does not exist. The function at d could be, excuse me, I keep wanting it to be d again. The function at f is equal to n. It could be equal at that point. I could color in the dot for n, or the function at f equals p. That would just be coloring this dot in. Or it could be that the function at f equals q, some totally other value, which would be like a point up here. All right, so I have a bunch of choices for the function, but the limit itself doesn't exist. I can't write it in this generalized form because the value n does not equal p. I get two different limits when I look from both ends. And this would be a jump function. You'd have to jump to go from one to the other. So the last scenario that we want to look at are infinite limits. So infinite limits happen whenever we have an asymptote. So if you have an asymptote, meaning that there's no possibility of having a C point pop up someplace else off of the graph, like here or like here, and you don't even have a hole, what you have is an asymptote. You have an unresolvable issue with the function that you're working with. When that happens, limits, then the function, as they get closer and closer and closer to the asymptote, go off to infinity. So say on the left hand side this one goes off to infinity, in the positive infinity, but on the right hand side it also goes off to positive infinity. Then what you have is a left-handed limit that equals infinity and a right-handed limit that equals infinity. So you would write the limit as, and in this case you can get away with writing, let's get a variable, a letter here, d, g, m. Let's go with m. So the limit as x values approach m from the left or the right of this function equals positive infinity. And I can write the generalized form because the same thing is happening from both the left and the right. So the other case where I could write it in the same generalized form would be the limit. Let me draw a picture of it. A case where you have an asymptote and you have a function that goes off on both sides toward negative infinity. So you could write the limit as x values approach n of this function equals negative infinity, because that's where this graph is headed off. That's the limit of the edge of this line. If you followed it on forever, you'd get closer and closer to negative infinity y values. And then the other cases are left and right. I'm only going to draw one. If I have an asymptote at P, point P, where on the left-hand side it goes to positive infinity, but on the right-hand side it goes to negative infinity. Now I have to write both limits because I can't write the generalized form. Both sides are doing something different. So I would have the limit as x values approach P from the left of this function equals positive infinity, and the limit as x approaches p from the right of this function equals negative infinity. And obviously I could switch these around and put a negative infinity here and a positive infinity here if the opposite thing happened. So let's do a quick review of finding vertical asymptotes. So f of x equals 1 over 2 times x plus 1. In this case, we know that the denominator can't ever be 0, and since we have a variable, that means we probably have a value that would force the denominator to be 0, and we have to eliminate that value from our function, from our domain. So we want to say that 2 times x plus 1 can't equal 0. Well, in this case, we're talking about factors, right? We would have 2 can't equal 0, but 2 never does equal 0, so that's redundant. But x plus 1 can't equal 0 either. And so that means that x can't equal -1. So we know that we have a vertical asymptote at -1. Of course, if I had some kind of factoring I could do in the numerator and factoring I could do in the denominator and cancel the problem, then we would know we have a hole. But in this case, it's clearly a vertical asymptote. Another place to find a vertical asymptote might be in trig functions. We know that a lot of the trig functions have them. So f of x equals cotangent of x. So in this case, cotangent of x, it's sine and cosine are the only trig functions that have really pretty curves that just go on and on and on forever. And the cosine on the same graph would look like, I always have a hard time lining those up, right? And that would also go on and on forever. So cotan isn't a sine and cosine. It's actually one of the functions that we know has an asymptote, and it's easy to find the asymptote because we know that the cosine is the same thing as, the cotan is the same thing as the cosine of x divided by the sine of x. So every place on the unit circle where the sine of x equals 0, we're going to have an asymptote. So if I do the unit circle real quick and just look for a sine, well, sine is always the y values, and the only place where y equals 0 is when you have an angle on the x-axis. So at pi and 0, or I could say at 0 plus n pi, at every angle of a multiple of pi from 0 is going to have a vertical asymptote. So on the graph, if you were going to graph the cotan function, you would go right in here and say there's a vertical asymptote at 0, and there's a vertical asymptote at 1 pi, and there's a vertical asymptote at -1 pi, and at 2 pi, and on and on and on. So let's look at another case. This will be a direct example. We want to find the vertical asymptote of All right, so first things first, we see there's a lot of factoring, and it looks like we're going to get some x minus 2's, and I'm probably going to get something like x minus 2's up here. And so factoring would be the first place I'd want to check. So let's go ahead and factor the numerator. This is going to be x. Well, for a plus 2, I'm probably going to want 2 and 4 to get a -8, and I'm going to need a positive 4 to get the plus 2, so x minus 2. And then down here, I have x plus 2 times x minus 2. If I cancel those, that's great. I got rid of part of the problem at the f of 2, but check it out. I didn't really get rid of all of it. I still have a problem. I have a hole at x equals 2, but I have an asymptote at x equals -2 because x plus 2 is not allowed to be 0. So x is not allowed to be -2. So on the graph, and I am not sketching this function, I'm just making an example. At -2, I'm definitely going to have an asymptote, and then the graph will do whatever it does. So say this graph comes up and goes off toward infinity, but on the other side it does something like this, where there's a hole at x equals 2. Because the excuse me, did I do that backward? Nope. At x equals 2, there would be a hole, and at x equals -2, there would be an asymptote, because I was able to resolve the factor that would have caused an asymptote at x equals 2. So let's label what this would be. I would say in this case that the limit as x values of this picture, and this isn't the right picture, but I know it's the right concept because I've already done the work here, and so I can even evaluate it. Let's even erase the picture so we're not getting confused by that. Okay, so the limit as x values approach +2, right, of f of x is merely undefined or does not exist, right? It's just a hole. But the limit as x approaches -2 from the left, and in this case I actually do know this to be the case for this function, as you approach -2 from the left, you're approaching an asymptote, and from the left-hand side it goes off to -infinity. And for the same function, the limit as x approaches -2 from the right of f of x approaches +infinity. So you really have a graph that looks like this, and this is the legitimate graph. So that would be a combination, or that would be a situation where you end up with a whole and a asymptote. Asymptotes lead to infinite and negative infinite limits. And actually, I should go back and clarify this. That was a little mistake on my part, just trying to make a point. The limit actually exists at, it's someplace just less than 2. So the limit actually exists, let's call it L. But the function of x doesn't exist, or the function of 2 does not exist, because there's a hole in the function, but the limit still points directly at L. So the limit exists. Okay, so let's do a couple of direct examples and introduce some properties at the same time. So example 2, suppose I have the function f of x equals 1 over x plus 3x. So this is really a combination of functions. So I could call this the g of x, and I could call this the h of x. And so really what we're looking at is what is the limit as x values approach 0 of the g of x plus the h of x. I'm just adding 2 together. Okay. Well, in this case, what happens is you can see that the limit as g of x, so let's break it down, it equals the same thing as the limit as x values approach 0 of g of x, and we've seen this before, plus the limit as x values approach 0 of h of x. And so the limit of g of x at 0 equals infinity, right? Because we have a rational function, and we know that the parent graph of 1 over x looks like this. And so if I approach from the left, it equals infinity. If I approach from the right, it equals infinity. If I approach from the left, it equals negative infinity. So let's just deal with one side in this case. So let's look at what happens to the limit as x values approach 0 from the right. And so from the right and from the right in both of the sub-functions. Well, the limit as x values approach 0 from the right of g of x equals infinity, right? Because it just zooms off to infinity here. So that equals infinity, plus the limit as h of x approaches 0 from the right. Well, that's just 3x, right? So that just equals 0, or it approaches 0. And so we can just say that that equals infinity. And there's a property in this. These are the properties of infinite limits, that if you're given a limit of some function of x, so as x values approach c of f of x, approaching infinity or negative infinity, and you have another limit as x values approach c of g of x, approaches some value L. So what we're talking about is if you combine a constant limit to or a existent limit, or a limit at a value with an infinite limit, what happens? And we saw in this example that the limit as x approaches c of f of x plus g of x, even if it's a big number, even if it's 10 million, it's not enough to really change infinity or make infinity now suddenly a constant value. It's going to equal infinity. If you combine by addition or subtraction infinity and some other constant value, you still get infinity. And this is called the sum and difference law, or the sum and difference property. Okay, another property then would say, well, let's use almost the same thing. Let's say that f of x, well, let's not use f of x now. Let's say that h of x equals 1 over x times 4. Okay, so now you have f of x equals 1 over x, and we're going to keep f of x being equaling infinity, right? We've already talked about that. 1 over x is infinity, and the value of 4, the limit as x values approach 0 in this case of 4 is just 4 because that's a constant function. So I would have, if I wrote it out, the limit as x values approach 0 of f of x, this being f of x, times g of x, this being g of x, equals, well, the limit of 1 over x equals infinity, and the limit of 4 equals 4. And even if I'm multiplying infinity by 4, it's still infinity. It's not going to change infinity to multiply infinity by 4. And so that is also equal to infinity. So the generalized rule says that the limit as x values approach c of f of x times g of x equals infinity times L just equals infinity. As long as infinity is greater than 0. If infinity is less than 0, then it would equal negative infinity. I'm sorry, if L is less than 0, then it would equal negative infinity. So that's the product rule. Now, the quotient rule is where things get really interesting. And that says the limit as x approaches c of g of x over f of x. So what do we have here? Well, we know that the limit as x approaches c of g of x equals L. And we know that the limit as x approaches c of f of x equals infinity. So what do you think? Can you have infinity in the denominator? Of course you can. And what ends up happening is this equals 0. And the reason it equals 0 is if you get bigger and bigger and bigger and bigger values in the denominator, then the whole value is going to become smaller and smaller. A short example of that is that if I look at the number 1/2 and compare that to 1/20th, the bigger 20 in the denominator is a smaller number. 1/20th is much smaller in value than 1/2. Same thing with 1 over 2,000, right? And so the bigger and bigger and bigger and bigger that these values in the denominator get, the closer and closer you get to 0. And you can't really get bigger in the denominator than infinity. And so with the quotient rule, when you're dealing with a function that breaks down to or combines to give you some value in the numerator and infinity in the denominator, that equals 0. Now, let me give you a little caution. Infinity over infinity, we don't know yet. Like, we're going to do that, but we don't know yet. So right now you have to just say that's like crazy talk. And one last thing, and I promise it's the last thing. I know the video is getting long, but I think it's important that you get these examples. What are you going to do if you have something like the limit as x values approach 2 from the right of 1 over x minus 2. So first thing we want to see is, can you plug in 2? And you can't because you're going to get 0 in the denominator. Then you're going to see if can you resolve it. Is it removable? And it's not, because I can't do any factoring or canceling, so it's not removable. So you know for a fact, a living fact, that right now at 2, and we're only going to look at from the right, that this limit equals infinity. Right? Because there's an asymptote. So it's going to go off to positive infinity or it's going to go off to negative infinity. How do you figure out which one? Well, you can always graph it on your calculator, or you can look at numeric values. But another way to do it is just figure out whether you're dealing with positive or negative values as you get close to it. So you could put in something like, let's see, let's plug in, let's find out what, if we know that the asymptote is at 2, what happens if we put in x equals 3 into the function? So the f of 3 would be 1 over 3 minus 2, which is 1 over 1, which is 1. Most important, it's positive 1. And so positive 1 tells you that this function is going to curve off on the positive y values. You may be a little nervous that it crosses over at 3 that way. So in that case, you could choose something a little bit closer to C, right? So what happens if it's at, let's see, check the f of 2.5, 2.5, right? So that's going to give you 1, and then 2.5 minus 2 equals, well, that's still a bigger number than 2. Take away 2 is still going to give you a positive value. Or what about the f of 2.25 equals 1? So that's 2.25 minus 2 equals, well, the numbers are just getting bigger and bigger and bigger in front of the minus 2. So that means that you subtract, or excuse me, they're getting smaller and smaller. Hang on. They're bigger than 2, but they're getting closer and closer to the asymptote, closer and closer to the asymptote, but they're still remaining bigger than the subtract 2. And so you still have a positive value. So that's how you would tell that it's positive infinity rather than negative infinity. So your practice set for tonight should be page 88, numbers 1 through 4, 9, 18, 29, 32, 35, and 41.